Good morning. All right, we are in the middle of momentum, or I guess, yeah, sure, middle of momentum. Sounds good. So we'll continue with that. We'll just ease into it a little bit here with just some simple stuff with momentum, change in momentum, and then start talking about how we use momentum when we solve problems. Just a couple of reminders. We have a 3-day weekend coming up. I know that doesn't affect us, but Monday is a holiday. And then our exam is a week from tomorrow. So Friday, what is that, the 29th? A week from tomorrow. Okay, so find the momentum of the ball. Momentum is just mass times velocity. 24 units are kilogram meters per second. And don't forget, it's a vector quantity. So a complete answer has magnitude and direction. All right, one more. Okay, straightforward. Now let's find the change in momentum. Just make it a 2 kilogram object every time. Initially moving 3 meters per second to the right, something happens to it, then it's moving 5 meters per second to the right. Find the change in momentum. And do it, you can do it numerically, but do it with vector addition also. It's good practice. So if we just do this numerically, we have to pick a positive direction. I'll call the right my positive direction. Then I can say that P final minus P initial is 2 times 5 minus 2 times 3 4 kilogram meters per second. In the positive direction, it's positive. Or we can do our vector addition. So our final momentum would be this one. A vector that's proportional to 10. The final momentum is 10. And our initial momentum was 6. I'll use green. But we're subtracting it. The opposite of P initial. And when I add those together, I have to get delta P. Oh, I'm one short here. That's my problem. There we go. Okay. We'll do another one. Two kilograms, moving at 3 meters per second. And then it comes to rest. So if I did it numerically, I can define the right as my positive direction. My final momentum is 0. My initial momentum was 2 times 3. So I get -6 as my momentum, as my change in momentum. And I can do it vectorially. My final momentum is 0. My initial momentum is 6. So the opposite of that would be to the left. My change in momentum is 6 to the left. Now we have an object moving to the right at 3 meters per second. Something happens, a force acts on it, and then it's moving to the left at 3 meters per second. What's the change in momentum? First, numerically, we've got our final momentum, which is 2 times a negative 3. And we've got our initial momentum, which is 2 times positive 3. We get a negative 12 kilogram meters per second. Or we can do it vectorially. We've got P final. We've got the opposite of P initial. And we add those two together. And we get delta P. 12 kilogram meters per second to the left. So there's a really big change in momentum there, twice as much as case 2. The object came in and stopped, and so that's a certain change in momentum. But when it comes in, stops, and then comes out in the opposite direction, that's a huge change in momentum, right? It practically doubles it. In this case, it did double it because it came out with the same speed. It doesn't always come out with the same speed after a collision, but it makes the change in momentum much bigger. So was the force on our object in case 2 larger, or was the force on our object in case 3 larger? Sometime between our initial and our final state, a force acted on this thing and caused its motion to change. It was moving 3 meters per second, then it stopped. A force acted on it and caused it to stop. In the next case, it's moving at 3 meters per second, and then it's moving at 3 meters per second in the opposite direction. A force acted on it and changed its motion, and it was going from 3 meters per second this way to 3 meters per second that way. Which case was the force bigger? In case 2 or 3? In case 3, right, it had to be bigger in case 3. It produced a much bigger change in motion, a bigger change in momentum. And where did that force come from? It came from whatever it interacted with. Maybe there was another ball sitting there at rest, and it collided with it and came to rest, and that first ball that was just sitting there then takes off. Or it came in, collides with it, and bounces back, and that first ball takes off. The force came from the interaction with the object it collided with. So in which case does the object come out with a bigger speed? When our incoming object stops, hits it and stops, or when our incoming object hits it and bounces back? Let's see. Oh, wait, I don't want to do that. Here. Okay, let's see. This is a happy ball. As you can see, it likes to bounce. This is a sad ball. It doesn't bounce. On my pendulum, I have a happy ball on one end and a sad ball on the other. The happy ball makes the pendulum bounce back after it strikes something. The sad ball makes the pendulum stop when it strikes something. Now we'll lift the pendulum up and have the sad ball strike this block. Let's mark the location and try it one more time. The sad ball is the side that's hitting the block, so the pendulum does not bounce back after striking the block. Lifting the pendulum to the same height each time, we get a similar result. Now we'll turn that pendulum around so the happy ball is facing forward. Now the pendulum will strike the block and bounce backwards. Lifting the pendulum to the same height, we see how far the block goes. Let's check it one more time for consistency. Okay. So bouncing produces a much bigger change in momentum, a much bigger force between the objects, and the object that gets hit comes out with more speed. I am told that there are some martial arts techniques where the person bounces their fist off of whatever they're trying to hit to create this effect. But it's very hard to do, because what happens when you think about bouncing your fist off of something, usually you let up a little bit and you don't end up not hitting it as hard. It takes a lot of practice to really bounce your fist off of something. So what do most martial arts, or what do most techniques teach when you're trying to hit an object and make it go farther? Baseballs, golf balls, even fist fights, usually they tell you to do what? Follow through, right? Have you heard that? Follow through. So the idea there is you don't try to stop your swing. When you're hitting a baseball, you don't try to stop the bat right when you hit it. You swing through it. And by doing that, when you make contact, if you continue to try to swing the bat, it changes the time interval a little bit. It increases the time interval a little bit that the bat is in contact with the ball. When you're swinging a golf club and you follow through, you can try to increase that time of contact a tiny bit. If you try to bounce off of it, the golf ball is so light, and a baseball is light compared to a bat, and you're trying to bounce off it, you end up not hitting it anywhere, right? But if you follow through, you can increase the time of contact. And that we learned last time. Where's our, come on. What's going on? There we go. We learned last time impulse, momentum, right? Impulse is force times time, and that equals the change in momentum. So if you want the ball that you're hitting to have a big change in momentum, you want to hit it with the biggest force you can, and you want that force to act on the object for the longest time period you can make it act on it. So instead of it acting on it for a tenth of a second, if you can make it act on it for 2/10 of a second, you've doubled the effect of that force. Okay, that's the idea with impulse. Follow through I don't know. Question about the time of contact for the bouncy ball versus the sad ball. The fact is that the change in momentum has to be twice as much when the object bounces back, right, with the same speed it came in at. So the change in momentum is twice as much. And if it comes out with less speed, it's a little less than twice, right? But almost. And that is fixed, right? And that fixes the change in momentum of the object that's being hit because they're always equal and opposite, right? That's what we saw yesterday or last time. So if the object coming in has a certain momentum, a certain change in momentum, the other object has to have an equal and opposite change in momentum because all the forces are internal to the system. And that tells us, even we can ignore time completely. That tells us what has to happen to the object being hit, the change in momentum of the object being hit. All right, I got one more of these. My 2 kilogram ball, 3 meters per second. And then it's going over here, 3 meters per second. I think this one's easier to do vectorially. Delta P is P final minus P initial. I know each one of these are 6, right? So that means that the magnitude is 6 squared plus 6 squared square root. And the direction is at a 45-degree angle. Sometimes doing vector addition is the easier way to do it. Okay, we good with that one? Change in momentum is at a 45-degree angle with that magnitude. Final minus initial. Let's look at the direction of the impulse. So we've got our object moving 3 meters per second. And then it's moving 7 meters per second the other way. What was the direction of the impulse? Correct. The vector is momentum, which is mass times velocity, mv. We're looking for the direction of the impulse. We can get that two ways. We can think about force times time. Whatever the net force is that acted on this between our initial state and our final state, that's the direction of the impulse. What direction was the force that acted on this object that caused it to slow down? It's moving 3 meters per second to the right, caused it to slow down, turn around, and come out moving at 7 to the left. The force had to be pushing on it to the left. So the impulse has to be to the left. Or you could say, instead of saying impulse is the average force times the time, say impulse is the change in momentum, and look at the change in momentum there. You'd get it was to the left. Now we've got our object coming in, same object, but now it comes out moving at 4 meters per second in the upward direction. So a force had to push on this thing to the left to slow it down and stop it. It no longer is moving in the x direction. There had to be some force pushing back on this to the left. Impulse in the x direction. And then there had to be some force that caused it to start moving in that direction. I'll call that impulse y. So the net impulse is something like this. There must have been a force acting on it in that basic direction. Part of that component, one component of that force slowed it down and stopped it in the x direction, and the other component got it moving, gave it momentum in the y direction. Or you can think of it as the change in momentum in the x direction is to the left, and the change in momentum in the y direction is up, and get the directions that way. Okay, so just some fundamental stuff we're going over here. Momentum, change in momentum, impulse. Now let's get into how we use this. collisions. That's usually when we use momentum. And sometimes it's not easy to spot a collision. So I've got three basic things I look for. And if it falls into one of these categories, it's a collision. The first one is when something blows up, when one object becomes multiple objects. So the object blows up. Now, if you have an object sitting there and it blows up and parts are flying off in every direction, is mechanical energy conserved? Is the kinetic energy the same before and after? Are they the same? No. You've got an object sitting there at rest, let's say, zero kinetic energy. Then you've got parts flying in all different directions. Lots of kinetic energy, right? Where did that energy come from? Well, from an explosive. Maybe it was stored chemical energy in an explosive. Maybe you have two people standing on ice skates in the middle of a frozen lake, not moving, no kinetic energy. Then they push off each other and they're both moving in opposite directions. Lots of kinetic energy. Where did that energy come from? It came from their muscles. They've converted some biological processes, converted something, some energy. It released some energy into the system, right? Chemical energy into the system. But if you have an object sitting there and it's not moving, it has no kinetic energy. If it blows up and pieces are flying everywhere, lots of kinetic energy, right? But even though the energy is not the same before and afterwards, and we might not be able to account for it if it comes from an explosive device or something, and we can't account for that. If it comes from something that we know how to account for, maybe it comes from a spring. Maybe we have two blocks pushed together with a spring and held there, and then we release them, and the spring pushes them apart. Then we can calculate how much energy came into the system from the spring. We might be able to calculate that. But a lot of times with these, we don't know how much energy was added to the system. But we do know that the momentum before and after the explosion has to be the same because all the forces come from within the system. So I think you're starting to see now that momentum can be a pretty powerful tool. How about this one, when multiple objects become one, things stick together. So you've got a box, a lump of clay. It hits the box and sticks to it, and the two things move together. Or if you want to go back to our ice skater example, you've got somebody standing on their ice skates, and somebody's skating along really fast, and they grab them and give them a bear hug, and the two skaters move together afterwards. Something like that. Two objects sticking together and then moving as one afterwards. Sometimes that happens in automobile accidents. The cars crash together and the metal gets intertwined, and the two cars stick together and move off in some direction, stuck together. In this case, Kinetic energy, is it the same before and afterwards? Do we know? The answer is we do know, and the kinetic energy is not the same before and afterwards. Some of that kinetic energy gets dissipated into other types. When things crash together, sound is given off, right? That's a little bit of energy, not a lot, but a little bit. And when things stick together, we call that deformation. It's kind of the ultimate deformation. We know for certain the kinetic energy afterwards is not going to be the same as the kinetic energy before. When things stick together, we usually have less kinetic energy at the end. When things blow up, we usually have more kinetic energy at the end. But they're not the same. Metal, when metal gets bent, things deform. Heat might be generated. So we know for certain when things stick together, the kinetic energy will not be the same before and after the collision. But what is the same? Momentum, right? If there are no external forces acting on our system, the momentum will be the same before and afterwards. And then what's the last case here is what you probably thought of as soon as I said collision. What did you think? You thought something like billiard balls bouncing off of each other, probably, right? That a lot of times that's the first thing that comes into mind. So objects bounce off each other. All right, what am I going to ask you? Is the kinetic energy initial, is it the same as the kinetic energy at the end? The answer is we don't know. It might be the same, it might not be. There are cases where things bounce off each other and the kinetic energy is the same before and after the collision. We give that a very special name. We say it's elastic collision. But there are also cases where things bounce off each other and the kinetic energy is not the same before and afterwards because of sound that's given off. The surfaces heat up a little bit when they collide with each other. Even hard objects that collide, the surfaces heat up a little bit. So we don't know. It might be the same, it might not be. We would need more information. So if you look at a collision problem in the book or on an exam and the objects bounce off of each other, we don't know if it's elastic or not. How do you know? There's only two ways. You're told it's elastic. Sometimes it says in the problem, in this elastic collision, blah, 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 right? Then you know kinetic energy is the same before and afterwards. Or you calculate it, right? You solve for the velocity before and afterwards, and you find the kinetic energy before and the kinetic energy afterwards and see if they're the same. Those are the only two ways you know. So it could be, in this case here, it could be that's elastic. May be different. That's inelastic. So three types of collisions. The tricky one is the third one, when the objects bounce off each other, because we don't know if it's elastic or not. Might be elastic, might be inelastic. We don't know. We need more information. Never assume it's elastic. If you're not told, assume it's inelastic and go from there. But in 1 and 2, we know for certain it's inelastic. The kinetic energy will not be the same before and after the collision. Okay, let's do a couple of examples. starting with these guys. We've got these two carts. Before the collision, one is twice as massive as the other one. They both are moving at the same speed, 10 meters per second. They collide and stick together. What's the final velocity? I'll give you a hint. It's one of the first five. You can move. Can't you move the pole? Is that better? It's not the pole. Let me see. Still there? Thank you. Okay, let's take a look here. We've got, I'll go through it real formally here so you kind of start to build some good habits. Initial momentum. What's going on here? Come on. Is equal to final momentum. This is a vector equation. I'll define the right as my positive direction. And so initial momentum is going to be the initial momentum of m and the initial momentum of 2m. And at the end, it's just the combined m. Final momentum is just m plus 2m, right? They're stuck together. There's only one momentum at the end. So initial momentum of m is its mass times its velocity. And the momentum of 2m is the mass times the velocity. Vectors, remember vector equation. And at the end, it's going to be 3m times v final. That's what we're searching for. So we get minus 10/3. We all right with that? Okay, this one, they're initially at rest. They're blown apart by an explosion. The big one moves to the right at 10 meters per second. The little one moves to the left at what speed? I don't have a poll for this one, sorry. So P initial equals P final. (20 meters per second). Good. What is the initial momentum? This is a vector equation. Define a positive direction. Initial 0. And at the end, it's going to be the momentum of m plus the momentum of 2m. So this is going to be m times v, and this is going to be 2m times 10, and we get we get v final is negative 20. 20 meters per second to the left. They asked for the speed. They asked for the speed. 20 to the left. Or negative 20 and define what your positive direction is. Don't tell me negative 20 to the left. I don't know what that means. Be clear. All right, let's squeeze one more in here and then we'll take a break. Got a rocket ship parked at rest in space. Suddenly explodes into 3 equal mass pieces traveling in the directions shown. If the piece traveling upward has a speed of 150 meters per second, what are the speeds of the other 2 pieces? Actually, I'll tell you what, this might take a little bit longer. Let's take a break now. If you need something to think about for the next 10 minutes, you can think about this, but it's probably better you get up and stretch your legs. I'm going to pause the recording, take a 10-minute break, and then we'll come back and think about how to do this problem. We're back. So let's think about this problem a little bit. We've got something just sitting at rest in space. It blows up into 3 equal mass pieces, 1, 2, and 3, as shown. How do we tackle this problem? This falls under our definition of collision, right? Something blowing up into multiple pieces. We know there's started out with 0 kinetic energy. It ends up with a whole bunch of kinetic energy. So unless we can somehow know how much energy was added in that explosion, energy conservation isn't going to help us, right? We don't know how much energy was added. So can't do that. But momentum will still be conserved. That's a vector equation. And what do we do typically when we have vector equations? Break them into components. So if the momentum at the beginning equals the momentum at the end, then the momentum in the x direction at the beginning must equal the momentum in the x direction at the end, and the same is true for the y direction. So we typically, when we have something like this, multiple dimensions, we split that up. We say momentum initial x is momentum final x. Call the right my positive direction. Momentum initial y is momentum final y. Call up the positive direction, pick a direction. And so let's do the x direction first. I'm calling this my x direction and this my y direction. And let's call this one object 1, and this one 2, and this one 3. What's our initial momentum in the x direction? 0, right? Nothing is moving. So that's got to equal the final momentum of in the x direction for 1, plus the final momentum in the x direction for 2, plus the final momentum in the x direction for 3. Object 1 is moving straight up. It has no x momentum at the end. Object 2 is moving in the negative direction. So I'm going to put a negative sign here, and it's the mass times the velocity in that direction, the x component of the velocity. So that's going to be, I'm going to call the velocity v2, and it's going to be the cosine of that angle. And 3 is going to be positive mass times velocity times cosine. And the masses are the same, the cosines are the same. So what does this tell me? It tells me that V2 and V3 are the same. Didn't give me a lot of information, but that is an important piece of information. Maybe as you start to get familiar with these types of problems, you'll spot stuff like that. But that's okay. It tells us, the equations tell us. So we know that V2 and V3 are the same, and we just need to figure out what it is. Now let's take a look at the momentum in the y direction. Initial momentum in the y direction is 0. Nothing's moving. Then we have the momentum of 1. I'll write it out here. We've got the final momentum in the y of object 1, the final momentum in the y of object 2, and the final momentum in the y direction of object 3. And object 1, we know it's its mass times, I'm just using lowercase m, I'll use mass times its velocity was given. The other two are both the same, and they're both going in the negative direction, so it's minus 2m, and the sine of 14.48. Oh, v, I need a v in there, v. 2m v sine 14.48. And I get 75 over the sine is v. It's about 300. Okay, so you see how we would do this if we had a two-dimensional collision, and we often have two-dimensional collisions. Think about a pool table, right? A billiard table. The balls come in, collide, and move in 2 dimensions across that surface of that table. And we could use these techniques to solve those problems. Okay, let's work through a few examples, and we'll use momentum, and we'll look and see if the kinetic energy is also conserved or not, whether the collision is elastic or inelastic. So we've got our carts. This one is at rest. This one is moving. And at the end, A is bounced backwards. And B, we want to know, what is B doing? VB final, what is it? The mass of A, we have to know the masses, don't we? Mass of A, let's go with 2 kilograms. And the mass of B, how about 6? Okay. So first thing we're going to do, find the final velocity of block B. This is a case where 2 things bounce off of each other. Do we know if it's elastic or not? We do not know. It might be elastic. The kinetic energy might be the same before and after the collision, and it might not be. How do we know? Well, we're going to find out. We're going to solve for the kinetic energy before and afterwards and figure it out. But first, we're going to have to find the final velocity without assuming that it's elastic. We will use momentum. P initial has to equal P final. I'm going to call the right my positive direction. That means that I've got the initial momentum of A right? And I know B is not moving initially. That was 0. So I've got 2 kilograms times 4 meters per second, and that's in the positive direction. At the end, I've got 2 kilograms times negative 2 meters per second. It's moving in the negative direction. 6 kilograms times VB final. And VB final has to be positive 2. So it's moving to the right. And is the collision elastic or inelastic? Find the kinetic energy initial. No, I used A and B, didn't I? Kinetic energy of A plus the kinetic energy of B. 1/2, what was A again? 2 kilograms. 4 meters per second. $16 joules. And at the end, that's a 12 plus 4, 16 joules, right? So in this case, it happened to be elastic. The objects bounced off each other. We didn't know if it was elastic or inelastic. We weren't told. So we had to calculate it out. Turns out it was elastic, but that's not always the case. All right, let's do another one. Okay. Now, do we know if this is elastic or inelastic just by looking at it? Yes. It's inelastic because they stick together. But let's just do the calculation, make sure. You can see it's usually a lot of energy that gets dissipated when things stick together. Okay, we good with this one? They blow up. We know for certain it's inelastic. I just did the little thought experiment there. Initially, it's 0. At the end, it's got kinetic energy. Stuff's moving. Has to be inelastic. 0 and something are not the same. And then momentum conservation. Use that. be careful of your signs. If something's moving in the negative direction, be careful to keep that negative sign, and you get your result that way. Okay, one more. Got A and B. Is that what you got? Okay, momentum conservation. Now these objects bounced off of each other. They collided and bounced off of each other. Do we know if it's elastic or not? No. So how do we know? We have to find the kinetic energy before and afterwards. Let's see, is it elastic or not? That's true, but they bounce off each other, right? They don't stick together. They just bounce off of each other. You're right, it doesn't bounce back. So our initial, I've got a 1/2 2 times 3 squared plus 1/2 3 times 4 squared. Okay. All right, let's do our typical momentum energy problem you'll see in textbooks. I call them all ballistic pendulum type problems, but let's just start with the ballistic pendulum, and then you'll see how they're similar. So a ballistic pendulum what happens is this is a device used to measure the speed of a projectile like a bullet. So you set up a pendulum. Say it's a block of wood. And we've got a bullet coming in. With some velocity. Then what happens is the the bullet hits that pendulum and becomes embedded in it. It gets stuck in there. And the whole pendulum now is swinging, right? It's moving up. And then at some later point, it comes to rest. But it's up high now, right? Okay, you understand what's happening? The bullet is coming in, hits that pendulum, sticks to it, and the two things go up until gravity slows them down, comes to rest, and we can measure the height, and we will figure out right now how we calculate the speed of the pendulum, the speed of the projectile, if we can measure the height like that. Can we, how can we solve this problem? Can we use energy? Can we look at the energy that the bullet has initially and the energy at the end and use that to figure out the velocity of the bullet? No, because why not? There's an inelastic collision in between. And we know lots of the kinetic energy of the bullet is going to be transformed into things that we cannot account for. When the bullet goes into the wood, it's breaking the wood fibers, pushing them apart, making a hole in the wood. There's friction. Lots and lots of heat is generated. In fact, I don't know if you've ever shot a bullet into a block of wood. The bullet melts. Usually the bullet melts. There's so much friction generated when the bullet going through the wood, so much heat that the lead melts. Okay, so lots and lots and lots of kinetic energy converted into heat, converted into transforming the wood, breaking the wood fibers, making that hole. We're going to have much less energy at the end than we had at the beginning, much less mechanical energy at the end than we had at the beginning, because lots of that mechanical energy was transformed into heat and other things. So we can't use energy going from the beginning to the end. Can we use momentum? Can we look at the momentum of the bullet before and look at the momentum at the end and come up with something that way? What is the momentum initially? Some big number, right? The bullet's coming in with lots of speed. What's the momentum at the end? 0, right? Nothing's moving at the end. The pendulum comes to rest momentarily. Why can't we go from the beginning to the end using momentum? Because the earth gets in the way. The earth reaches into our system as an external force and pulls on that pendulum and stops it from swinging up too high. I guess technically, if we could include the earth moved a tiny bit, but as far as we're concerned, the earth is an infinite mass. We can't use it in calculations like this. So we can't go from the beginning to the end using energy. We can't go from the beginning to the end using momentum. What do? We break this into smaller problems, smaller chunks, where we can use energy and where we can use momentum. And physics instructors love this type of problem because it tells us that you understand when you can use energy and when you can use momentum and when you can't and when you have to use one or the other. So where do I break up the problem? At the collision, the split second before and the split second after the collision. That's where I break up my problem. So I draw out what I call a timeline. I sort of already did it here for you. I call that my timeline. And we'll call this time 1, and this time 2, and this time 3. And what is time 1? Time 1 is the split second before the collision. Just before the collision. And time 2 is the split second after the collision. And if that time interval is short enough, then I'm going to justify using momentum, even if I might have an external force acting on my system. Like in this case, gravity is acting on the system. So as soon as that pendulum starts to swing up, as soon as it starts to swing up, gravity is pulling down on it. But if my time interval is a really, really short, just the instant that the collision takes place, from the split second before the collision to the split second after the collision. If my time interval is so short, then gravity doesn't have a chance to act on this thing as it moves. As that pendulum starts, the pendulum gets struck and starts to move, and then that's where I cut off my time interval, and I'm looking at the momentum conservation because gravity hasn't had a chance to stop that pendulum from moving yet, right? And then an instant later, the pendulum starts to go up, swing up, and gravity is pulling down on it, changing its speed, changing its motion. So we have just the split second before the collision, split second after the collision, and then some later time. In this case, it's some later time. It might be some earlier time. It might be both. You look at whatever the problem dictates. But the two that you always have on your timeline, the two instances, the two times you always have on your timeline, split second before the collision, split second after the collision. Yeah, we'll do it. So how do we get through this? In this problem, we'd be given, let me tell you what we would be given and what we're trying to find. So we're given the mass of the bullet, the mass of the pendulum, the height that thing goes up at the end, and the length of the pendulum. And what are we trying to find? V1, right? The speed of the bullet. So for this problem, we work backwards. We're going to go from time 3 to time 2. And how are we going to use, what are we going to use there? Energy, right? We know the pendulum is at a certain height and it's swinging down, and we're trying to find the velocity of the pendulum at the bottom. That's just an energy conservation problem. So going from 3 to 2, using energy. That'll tell us what V2 is. Once we know V2, how do we get through a collision? Momentum. So we can go from 2 to 1 using momentum. So let's do it. Yeah. We treat them as two objects that stick together. Okay, so we're going to go from 3 to 2 using energy. So the energy at 2 has to equal the energy at 3. Because we have no, if we include the Earth in our system, we have no external forces. There's no friction. We're ignoring air resistance. So our mechanical energy at 2 has to equal our mechanical energy at 3. At 2, what do we have? We have kinetic energy. And at 3, we have gravitational potential energy. And that's it, right? Nothing's moving at 3 at the end. It's all gravitational energy. And at 2, it's moving, but it's at its lowest point. So it's all gravitation, it's all kinetic energy. One half m v squared has to equal m g h. So we get the square root of 2gh as our velocity at time 2. That's the velocity of the pendulum plus the bullet, the split second after the collision, before gravity's had a chance to slow it down. Now we can go from 2 to 1 using momentum. So the momentum of the bullet plus the momentum at time 1 of the pendulum has to equal the momentum at time 2 of the bullet plus pendulum. And we know the pendulum is not moving initially. So this is the mass of the bullet times V1 has to equal the mass of the bullet plus pendulum times V2. And there we have it. We didn't need it in this case. Sometimes you're given you're not given H. When we do this in lab, you're finding you measure the angle, but what do you really need? You need H, the amount that it lifted up the center of mass. So you need the length of the pendulum in that case. But in this case, I told you what H was. Okay, let's do this. I'm just trying to make a point here. If we could get every person on Earth to stand in one place, the same place, and jump, we want to know how much, what's the velocity of the Earth in the other direction. So we've got the momentum of the people has to equal the momentum of the Earth, right? Or you could say the momentum initial is 0, has to equal the momentum final, people in one direction, Earth in the other direction. The magnitudes have to be the same, the directions have to be opposite. So this is the mass times the velocity equals the mass times the velocity. Okay, we want to really exaggerate this. Let's say every person is 100 kilograms. 220 pounds. Way overestimate, right? Because half the people are kids. A good percentage are kids. Okay. How many people? More than 7 billion now, right? Let's just call it 7 times 10 to the 9th. A little bit more than that now. Every year I do this, it goes up and up and up. Mass of the Earth. 6 times 10 to the 24 kilograms. Okay, the whole point of this exercise is to show you that 10 to the 24th is a big number, okay, a really, really, really big number. Velocity of the people. Let's see, let's pretend that every person on Earth is a star basketball player and has a 1 meter vertical leap, okay? Every person on Earth can play in the NBA and has a 1 meter vertical leap. So how fast would they be going when they leave the ground if they have a 1 meter vertical leap? I would use energy conservation. I think that's the easiest one. So 1/2 mv squared, that's the speed when they leave the ground. They have all kinetic energy when they're standing on the ground. When their feet leave the ground, 1/2 mv squared, and they eventually get up mgh, where h is 1 meter, right? The mass cancels out. The velocity is the square root of 2gh. So if h is 1, g is 10, this is approximately the square root of 20. So what do we get here? We get the velocity of the Earth. 107 times 10 to the 9th, square root of 20, that's a 20, over 6 times 10 to the 24th is approximately 10 to the minus 13 meters per second. What is that? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If we could get every person on Earth to stand in the same place, and they were all a 220-pound NBA player that could leap 1 meter into the air, and they all jumped at the same time, the Earth wouldn't do a damn thing. The Earth is big. So anytime the Earth gets in the way in our calculations, it messes them up. We can't really use momentum conservation anymore. Does that make some sense? That's why when the pendulum swings up, we can't use momentum anymore, because the Earth is absorbing some of that momentum, and the Earth is so big, as far as we're concerned, it's an infinite mass. Okay, we will end it here. I'll stick around for a little bit to answer questions, but I will stop the recording now.